Okay, so in our last lesson, we talked about 3 new pieces of terminology, and those new terminology were volume, current, and resistance. Where volume is the push in electricity, current is the rate of flow, and resistance is something that slows the flow. So these are all components of electrical circuit. If we take a look at our circuits down here, we have this circuit, our first circuit, has some sort of power source, a cell. It has a switch that's closed and some sort of load. In this case, this X is another example of a way to draw a light bulb. So you'll see me switching back and forth. It doesn't matter which one you use. So in this current, we have a voltage, which is the push, because that voltage comes in from the battery. It's the battery that pushes the charge. We also have a current because electricity is able to flow the entire route of the circuit. And if you remember, electrons will flow out from the negative and in towards the positive terminal of the battery. And I like to think of it as they're being repelled from other electrons in the battery, and they're being attracted towards this positive end. Okay, so that's how I like to think of it. They're being pushed out by repulsion. So as you know, we have our formula, resistance is equal to voltage over current, and we can easily rewrite that to represent the different variations here, which are, color V is equal to I times R, and I is equal to V over R. And they're all the same thing, but they're just written differently. And so because whenever we have a formula that looks like this, we know that these variables are related to each other. They're dependent on each other. If one variable changes, then it has the potential to change other variables. For instance, a high voltage and a low resistance will allow lots of current to flow. So let's look at our current formula. So I is equal to voltage over resistance. And if we have a high voltage of 30 and a low resistance of 2, then we have a fairly high current of 15 amps. And don't forget the unit. Over here, it's important to note that I'm not necessarily saying 30 is high and 2 is low, but they're just numbers to show you the relationship between how a high voltage and a low resistance provides you a higher current compared to a high voltage and a high resistance. So in this case, they're both high. So we have high, 30, it's still 30, and instead our resistance is 15 instead of 2. And so 30 divided by 15 is 2 amps. So obviously our current here is higher than our current here. And these sort of statements can be made about any of these, they're all the same formula, but any of the arrangements of this formula. So you should already know that series circuits involve one path for the electrons to travel, and parallel circuits involve more than one pathway for electrons to travel. So they split up into different paths. This Ohm's law relationship changes depending on if we're talking about series or parallel. So for series circuits, The current, remember current is I, is the same throughout. So the current total is equal to the current at any given point on the circuit. Okay, so we could have many different points. So let's say we have a circuit over here, and we have an ammeter 1, and we have an ammeter 2, and we have, sure, we can have a battery there. And so this would be I1, and this would be I2, and their current, the number, the value, would be the exact same here and here. Now, voltage is a bit different. Voltage is shared between each load, and the loads are always something that sort of puts resistance on a circuit. So here we have V1, that's our load, our first light bulb. And so we say that total voltage is equal to V1 plus V2 plus Vn. Okay, so N just means however many number of loads there are. It could be 1, it could be 8, it could be 3,000, whatever it is, the voltage is shared. So the sum of the voltages go towards our total voltage. Now remember, voltmeters are put in parallel. So over here, we're measuring total voltage because the volts comes from the power source. That's the push. The power source is the push. So that's where our voltage is coming from. And so if our VT is equal to 4, and there's only one load, then V1 is also going to equal 4. So now let's move over to parallel circuits. So in parallel circuits, the current is actually shared between paths. So if I'm writing a formula, then that's going to look like current total is equal to current 1 plus current 2 plus current 3, plus current n. Okay, so it doesn't matter how many different places we're measuring the current, it just means that the current is shared. Now, the reason that current is shared is because, remember, we have more than 2 paths for the electrons to flow. So if we have a total of 10 current here, and let's say 4 electrons go down this path, then we'll have 6 going down this path. So they're shared between the various splits that we have. So now let's think of voltage. Now remember, there's a relationship between voltage, current, and resistance. So remember how I've called voltage potential difference? So that basically means the amount of stored energy. So let's pretend that you are walking 30 kilometers, okay, which is a very long walk, and your friend is going to bike 30 kilometers. So you're both going to the same place in parallel, walking the same distance. The energy that you start your journey with is the same. Let's just say you have 20 energy, okay? Super random. And at the end, you're both exhausted. So you have 0 energy. 0 energy. So regardless of the route you took, your potential energy or your voltage is going to be the same, okay, along a common pathway. So we say that voltage is the same across any pathway. So V1 is the same as V2, is the same as V3, is the same as however many V's there are. So we have voltage being the same across a constant pathway. So here we have our two diagrams in tandem. And so you should notice that there are similarities and differences between series and circuit. You should also notice that their reactions to current are opposite one another. So in here, the current is constant, but in here, the current is shared. And over here, the same is true for voltage, where here the voltage is shared and here the voltage is constant. And this was all discovered, or maybe it was theorized, by a guy called Kirchhoff, and we call them Kirchhoff's laws. So, as we move into these next sort of problems, I call them the puzzle problems, you have to keep these laws in mind. And when I say these laws, I mean that current is the same and voltage is different for series. Current is different and voltage is the same for parallel. So let's work on a series problem first. So here we have a circuit. Our circuit has a cell and 2 ammeters, and here's a light that I've labeled load 1. So the question is, what is A2? Well, we know A1, so we can use our formula where AT is equal to A1 is equal to A2. So if we wanted to know A1, then we're going to use our current formula. Sorry, I should have used I. I, not A. A is the unit. I is the symbol. See, I make the same mistake. So I1, I2. And because we know I1 is 4A, so that means that I2 is also 4A. Now what about the voltage? When we're talking about voltage in a series circuit, and we know it's series because it's one path around, we can say that Vt is equal to V1 plus V2 plus however many V's there are. And so Vt is equal to 8V plus nothing because we only have V1 up here, so I put that 8 in here. So our Vt is 8. Here's another problem. Wow, does that look complicated? Don't worry though. It's not as complicated as you think. So, let's talk about the circuit first. There's a few things going on, and I have to admit this is not the most neat and tidy circuit I could have made, but bear with me. So we have one cell here, and it has 12 volts. So that would be Vt. In fact, I'll write Vt. Then we have a circuit that goes down. There's 2 loads, light bulbs, and then there's an ammeter after the fact. So it's still series. What's going on over here? Well, those are voltmeters. Remember, voltmeters, to measure voltage, have to be in parallel with the thing that it's measuring voltage. So the first question is, what is the total current? We know that we use IT is equal to I1 is equal to I2 is equal to however many I's there are. So IT is equal to I1, and I1 in this case is 6A. So our total current must be 6A, or 6 amps, because current is constant throughout a series circuit. Well, our next question is asking about V1. So it wants to know V1. The first thing you always want to do is write down our formula. So VT is equal to V1 plus V2. And we only have two V's here, so I'm going to leave it there. And I'm going to fill in any information that I know. So I know that VT is 12 volts. And I know that because our battery is that. That's where the push is coming from. Now here's V1 and here's V2. I do not have that information. What I do have is a resistance value. So what that means is I can come over here and use my ohms formula. V is equal to IR. Now I don't know V. In fact, I'm trying to find V1. I do, however, know I, and I is 6A. And I'm going to multiply that by the resistance of my voltage 1, which is 2 ohms. And so I got this 2 from just the information provided to me, and I got this from the information provided to me, but we also calculated it up here, sort of. And so I'm just going to complete that, and so that's going to give me 12 volts, and I know that the unit is V. So, okay, I did the problem, and then I realized that my numbers didn't work out, so I changed a few numbers around. So you may notice that my total voltage is now 18, so I've written that down here, and I've also changed my initial resistances. So R1 is 1, so I plugged that in there instead of our value beforehand. And so 6 times 1 gives us 6. Now, so we can just say that over here, we can just say that V1 is equal to 6V because we calculated it on the side. For V2, we know that VT is equal to V1 plus V2, so total volts is 18 plus 6V plus V2. If we rearrange that formula, then we know that 18 minus 6 is equal to V2, which is 12 volts is equal to V2. And we've already figured it out up here, but VT is equal to 18 volts. So there's a bit of math we can do with our series circuits and a bit of problem solving. Over here, I have one for parallel. Okay, I know it's complicated. Don't panic. Okay, in this problem, we have our cell right here, our power source, with a voltmeter around it, measuring a total of 10 volts. If we go around our circuit, we notice that it's parallel because there's two different pathways here. And here we have our load 2, and here's our load 1, with a voltmeter around load 1. And there are 2 ammeters here. So I've told you that our total current is 12. I should put a unit on that. And so it wants to know, the question that I made wants to know what A2 is. Well, let's go check out our formula. So because it's a parallel circuit, total current is equal to current 1 plus current 2. And here we have 2 ammeters, so I'm going to leave it there. Our total current is 12 amps, and our current 1, we've been told that it's 4 amps, and that's plus our current 2, which is what we're trying to find. So if we reorganize this, we get 12 minus 4 is equal to I2. And so 8 amps is equal to I2. So A2 is equal to 8 amps. Duh. Never mind that. Okay, so then we want to know voltage 1 and voltage 2. If we write out our formula, voltage total is equal to voltage 1 is equal to voltage 2. Those are the ones we care about. So we're told that voltage total is 10, and we want to know voltage 1 and voltage 2. And so that voltage 2, even though it doesn't have a voltmeter, we know that that would be it because this is designated as load 2. That's why it's important to label everything as 1, 2, 3, total, whatever. So if our total voltage is 10, that means our voltage for V1 is 10, which means our voltage for V2 is 10. And so that means we have 10 and 10 volts for both of these. So that's my lesson on how this sort of Ohm's law relationship can be applied specifically to series and parallel circuits, and we went through a few practice problems together. I will probably post some of these for you to try later. Good luck!